Have you ever really stopped to think about what it takes to store the data for something like YouTube or Gmail or Google Search? I mean, we're talking about a scale of data that is just, it's almost impossible to wrap your head around. So today, we're going to pop the hood and take a look at how Google's foundational storage systems have evolved over time. All right, let's get into it. Just to give you an idea of the scale we are dealing with here, look at this number, 10 exabytes. That's 10 billion gigabytes. And get this, according to Google, that's the size of just one of their Colossus file systems. They have lots of these things. It's an absolutely mind-boggling amount of information. So that really brings us to the core question, right? When you're operating at that kind of crazy hyperscale, how do you even build a system that can reliably and efficiently and, affordably store and serve all of that data? Well, the answer is actually a pretty fascinating story of engineering evolution. And that story starts with a system that was truly way ahead of its time. It was a pioneering piece of work called the Google File System, or GFS. You can think of this as the original bedrock that really made Google's early explosive growth even possible. Now, GFS was built around this really specific idea. Instead of using super expensive, high-end servers, Google said, you know what? We're going to build our system using huge clusters of cheap, off-the-shelf commodity computers. The big challenge then was to write software that was smart enough to make all of this failure-prone hardware actually reliable. The architecture behind GFS was, honestly, beautifully simple. You had two main parts, one single master node, and then hundreds or even thousands of chunk servers. Now, the master, it didn't store any of the actual data. Think of it like a library's master catalog. It just stores the metadata. It knows what file is broken into what pieces or chunks and which chunk servers those chunks live on. The chunk servers? They're the bookshelves, storing the actual 64 megabyte chunks of data. So, when it came to actually reading data, it was a pretty slick process. When a program needed a piece of a file, it would first ping the master and say, hey, where can I find chunk X? The master would look it up in its catalog and shoot back the addresses of the chunk servers holding that data. Then, and this is the key part, the client would go talk directly to the chunk server. It bypasses the master entirely. This keeps the master from becoming a bottleneck for the actual data transfer. Now, this design made a very deliberate trade-off. GFS was an absolute beast at high-throughput stuff, like the massive batch jobs Google needed to index the entire web. It could just shovel enormous amounts of data around really, really fast. But because of that initial chat with the master, it wasn't so great for things that were sensitive to latency. Stuff that needs an instant response, like loading your Gmail inbox. And that brings us to the system's Achilles heel. As Google got bigger and bigger, that single master node, which held all that metadata in its memory, just became a massive bottleneck. It limited how big a single cluster could get, and even worse, it was a single point of failure. If that one master server went down, the whole file system was basically offline. It was clear a new approach was needed. And that new approach, the successor system, is known as Colossus. This was a complete redesign from the ground up, and it's what powers Google today. Yeah, the official switch really happened around 2010. By that point, the limits of the old GFS design were really starting to hold Google back. So the company went all in on its next generation system, Colossus, which was built to solve the problems of the next decade and well beyond. So here's the fundamental change. Colossus completely threw out the idea of having one single master node. Instead, it brought in a distributed, scalable system for managing all that metadata. Yeah, it's more complex design, but it's also way, way more resilient. Okay, so where GFS had that one master, Colossus has a whole team of services working together. You can think of curators as being like the front desk librarians, handling quick requests like creating a new file. Meanwhile, the custodians are kind of like the archivists working in the back, making sure all the data is safe, duplicated, and always available. This distributed approach completely got rid of that single point of failure that haunted GFS. But Colossus had to solve a totally new problem. One that really came about because of how storage hardware itself was changing, this constant tension between speed and cost. You know this yourself. Over the years, storage technology has split into this clear spectrum. On one end, you have your super fast, low latency solid state drives, or SSDs, which are awesome for performance, but they cost a pretty penny. And on the other end, you've got the traditional spinning hard disk drives, or HDDs, which are incredibly cheap for storing huge amounts of data, but they are much, much slower. And that is the billion-dollar question for any massive data center. How can you possibly build a system that gives you that snappy, instant performance that users expect from SSDs, but while still taking advantage of the cheap, massive capacity of HDDs? I mean, you can't just put everything on SSDs, you'd go broke. Google's answer to this puzzle is a pretty amazing system they built called L4. The best way to think about L4 is as the brain of Colossus's storage system. It's this intelligent, automated caching system that's constantly dynamically deciding what data is important enough to live on that expensive SSD real estate and what can stay on the cheaper hard drives.
So, how does this automation actually work? Well, this is where things get really cool because this is where machine learning enters the picture.
Let's just walk through a simple read request. An app needs some data. It doesn't go straight to the storage. First, it checks with an L4 index. If that index says the data is hot and is already sitting in the SSD cache, boom, it gets read super fast. If it's not there, okay, no problem. It gets fetched from the slower hard drive. But, and here's the really smart part, L4 also pulls a copy of that data into the SSD cache, so the next time someone asks for it, it'll be lightning fast.
But L4 doesn't just use one simple rule for everything. No, it uses machine learning to apply different policies based on what the data is being used for. For some data, it might decide, okay, cache this on an SSD the second it's written. For other data, it might wait until it's been read once. And for other types, it might wait to see if it's read twice in a short amount of time before deciding, okay, this is hot enough to earn a spot on the expensive SSDs.
And it gets even more advanced than that. L4 doesn't just react, it actually predicts. By analyzing things like the file type and historical access patterns, how often similar files have been read and written in the past, it can decide to put a brand new file directly onto an SSD right from the very beginning. This skips the slow hard drive entirely for data it already knows is going to be in high demand. It's a proactive, intelligent system. So after all that, what are the big takeaways from this incredible journey from GFS all the way to this ML-driven Colossus system? Well, there are a few core ideas that really stand out. First off, you have to design for failure. The jump from that single GFS master to Colossus's distributed system is the perfect lesson. Second, you have to automate everything. At this kind of scale, you just can't manage all this complexity by hand. You need smart systems like L4 to make decisions for you. And finally, you have to evolve with your workload. GFS was perfect for its time, but as Google's needs changed, the system had to change with it. And that kind of leaves us with one last big question to think about. We've seen these storage systems evolve to handle more data, more reliably, and more efficiently. But now, as AI and machine learning are making the data itself more active and intelligent, what's the next step in the evolution for the systems that have to store and serve it? That's the next giant challenge on the horizon.